So it would appear that Drew is going to come to class at some point today, I would hope. We'll see. Yes, I know that. I meant to go here. So can you tell what's on my dress?
Yes.
Yeah, this is the one I got with your gift card you gave me for Christmas. You guys gave me this Faja gift card, and this is what I got with it. I was so psyched.
My friend went to a pawn shop with his parents and me and my other friends went with him, and because he found a geode.
Oh yeah.
We found a geode. The person got it open, and then we got like $200.
That is really cool.
Or like 500. Like I don't know how much we got. It was probably worth 500.
Yeah, it depends on the geode and the type of geode. Some are worth more than others, obviously.
Any price you get from them, it's probably about half of the real value.
That's true. Pawn shops tend to price a little lower.
Well, they do give you straight cash.
Yep, there's Jocelyn.
Wow. That's the best I can do. Pawn shops are probably a lot of people go to this. They can afford to buy, a lot of.
Yeah. Good morning, Jocelyn. How are you? Good.
Hi, Miss Danny.
Hey, how are you doing?
Good.
Good. All right. So I have your Q4 grades. So y'all may have seen I sent an email, and I noted in the email that so I dropped 2 test grades, right? I dropped your 2 lowest tests and I dropped your lowest lab, and that's supposed to be for the year, for the whole course. But my system was doing it per quarter because that's all it was showing at a time was 1 quarter in the grade book. So it wasn't giving you very accurate grades. So I took that out of the automatic grading. Well, it changed for some of you, but I took it out of the automatic grading. And then I went back through every assignment that was tests or lab for the entire year, and I found your lowest. Some of you don't even have like a lowest lab because maybe, or a lowest test or whatever, because maybe you got 100 on everything or whatever. That's a rarity, but occasionally it happens. So I'm going to send that out to you. So you, I mean, I already, I believe, sent that out to you so you could see what those lowest ones were. That went out, I think, yesterday afternoon. So everybody should know what's being dropped right now. Now, if something between, something happens in the 4th quarter that's lower than what I sent you, obviously that will replace whatever's already on that list. But I'm going to have to manually drop those at the end of course because I don't think it's going to calculate the way I wanted it to. So anyway, that being said, anybody whose grade was below a 70 at the end of any quarter, I've offered a recovery plan. So that basically means it's a way to catch back up, find what you're missing, learn the material, because sometimes things happen. People get sick, people get hurt, family issues, we're in the pandemic. So some people will be getting emails about that, but only if you have a 70 or below at the for a quarter. Yes, you had a question, Eleanor.
Oh yeah, I need to tell you something. So on one of the tests, tests, like it was basically like I put like the right answer, but I marked it as wrong because I accidentally added like a V in it or something.
Wait, let her finish that.
Because there was like only one answer to it, and I put it in, and I accidentally added an extra word. Like it was the or and.
Yeah.
Because people tell me to like if you put 2 things, put an and. So I put an and, and then it marked it as wrong.
It'll do that automatically because I can't put in every possible thing you all could write because it'll automatically grade if I know what it is. Like if it's a fill in the blank or a short answer. But I can't guarantee that the system is going to understand everything you could possibly write. So I usually put manually graded, and that means that I go back and look. So I go back after every test and I go back and look. If you take a test late, you may need to let me know that I need to go grade it because I don't get like a really big alert that says, hey, go back and grade this and check it. But if you turn a test in on time, I go through it with everybody else and I check it.
She also has to do the manual grading problem, but she also just looks back because she just puts a view.
Yeah, I do. I go back and manually grade it. And I usually give comments. So if you go back and look at that one, wherever it was, if I didn't fix it, let me know. But usually I can tell because sometimes people spell wrong or whatever, or they do like that. They put an and or it's funny because for the ones that are fill in the blank, it offers me a word option. So say the word is element. I'll put in like element elements. I'll try in all the wrong spellings of the element I can think of. I'll capitalize it. I'll put in like 15 options because it just saves me the time of going back if the system thinks you're right. So I give it all these options, but sometimes I'm just not creative enough. So today we are talking about galvanic cells and electrolytic cells. And if there's time, I have kind of a hilarious video that we can watch, but only if there's time. Today is keep your work in your binder. So if you still got it in your binder, that's good. But if you did a Rico or whatever, you just show them to me.
We don't have to turn it.
No, well, we're going to go over it, so you don't have to turn it in. All right, so there's a historical perspective that I want you guys to have when it comes to batteries, basically. So this is some extra stuff that wasn't part of your assignment, but I think it's interesting to know. So historical perspective is here on electrochemistry in particular. So here are some really interesting pictures, and I like the one at the bottom because it's like, what is going on? So it says Thales of Miletus, which was 640 to 546 BC, is credited with the discovery that amber, when rubbed with a cloth or a fur, acquired the property of attracting light objects. What's amber? Do you guys know what it is?
Is it like a jewel or something? That dried out.
It's what?
A jewel that dried out.
Yeah, sap that dried out is absolutely right. It's a semi-precious thing, but it's not a mineral like an amethyst would be, or lapis or something like that. It's sap from a tree that has dried out and it's become rock hard. And yeah, they do make jewelry out of it. Sometimes it has bugs captured in it, which is super cool. And that was like the premise of Jurassic Park, is that there was a mosquito or something trapped in amber and they were able to get the DNA and, yeah, that's amber. That's what we're talking about. And amber is the color amber, which is like a golden yellow color. Okay. So when he rubbed it with a cloth, it acquired the property of attracting light objects. So what does that sound like to you? You ever experienced that before? You rub something and then things get attracted to it? Yeah, static. That's exactly right. Static electricity. When you rub a balloon on your hair, Ella had the great example. So the word electricity comes from electron with a K, which is the Greek word for amber. Well, that's interesting, right? We've been using electron and electricity forever, and it goes back to the Greek word for amber. So then we have this guy, Otto von Guericke. And Otto von Guericke lived from 1600 to 1686. So now we're talking about, you know, by now, this is a big jump. So 460, 546 BC, we're talking 2,500 years ago. And now we're down to this guy who does this electrostatic experiment in 1675. So in 1675, there were already people living here, right? Yeah. So Otto von Guericke invented the first electrostatic generator in 1675. It was made of a sulfur ball, which rotated in a wooden cradle, and the ball itself was rubbed by hand and then charged, and that charged sulfur ball had to be transported to a place where the electric experiment was carried out. This sounds like a process, like a lot of work, but hey. So eventually, this cool thing happened. A glass globe replaced the sulfur sphere used by Guericke. And that's what's in the little black and white picture. And then later, large discs were used. So this guy on the right here, that big disc with the red center, sometimes you can see reproductions of those in museums. And so we're getting somewhere. We're starting to build some real kind of cool steampunk looking stuff. I mean, that's neat looking. Yes.
I'm just telling you, as he's looking good.
I know, he licks everything. It's National Puppy Day, so.
I was just telling you because in case you didn't want him doing it.
You know, I can't stop him. So,
I
probably dropped something on them from the table once or something, and he's like, oh, delicious. It is National Puppy Day. Yep, right. So now we have, you saying Happy Puppy Day? All right. We have this guy, Ewald Jürgen von Kleist, and he invented Leyden jars. So Leyden jars are a thing that you'll hear more about if you learn more about the history of electricity. So he was from 1700 to 1748. So he didn't live all that long, did he? And he invented the Leyden jar in 1745, and it stored electricity. So this is the first device invented to actually store it. There was no way prior to that to do so. So it contained water or mercury and was placed on a metal surface with ground connection. So what do you know about mercury? What's mercury? You guys remember? It's an element.
It's a dangerous element that you should not touch.
Ah, good point. So it is actually toxic if you absorb too much of it. It is actually in some of the newer light bulbs. Okay, so a couple of years ago, there was a big thing about how we're all going to use these new, what are they called? I can't remember the name of them. It's a specific type of light bulb. We were all going to use these new energy efficient light bulbs. We weren't going to use the old school incandescent ones anymore. And we were told we weren't even going to be able to buy them. People were buying them up like crazy. So there was, you can look it up. There is an entire website. It's some government page. I don't remember which one, where it gives you instructions for how to clean up if one of those light bulbs breaks. And it is like multi-page. You have to open all the windows and leave the room and all this. I mean, it's really crazy. But mercury used to be very common in thermometers.
And it's dangerous, so they removed it.
Yeah,
So it's pretty
yeah.
rare if you have one. You can sell it for a decent amount of money, but it's also really dangerous. So
Yeah, it can be toxic. And so mercury is a metal, but it is liquid at room temperature. So
wasn't it?
gallium is also the same way. I actually have some gallium upstairs, but you can put it in your hand and run it all around. And it's silver. Yeah, it's silver and it's liquid at room temperature, which is really cool.
Silver is liquid at room temperature?
No, gallium is silver colored. Yes.
Wasn't mercury used like very super commonly a
Mhm.
while back?
Yes.
And once they discovered it, they stopped.
Yes. So mercury used to be very common. It was used. Yeah, it was used. So mercury was used in thermometers. Any thermometer that has that silver line inside of it, not a red one. The red ones are alcohol. The silver ones are mercury. And I actually exploded one once. Here comes Senya. I actually exploded one once on a light bulb because I was a kid and I was messing around and it blew mercury all over the place and my mother was not happy. But mercury was also used as a preservative in stuff like a long time ago. It used to be in vaccines. It's not anymore. It also used to be in amalgam filling they use in teeth. Not anymore. And it has gotten, because we've used it, has polluted the environment and it's gotten into fish in the ocean. So they say, like, if you're pregnant, sometimes they recommend that you eat the little fish, but not the big fish, because the big fish eat the little fish. So they amass more mercury as they go, because they're up the food chain. So like tuna, for example, or mahi-mahi or bigger fish, but like salmon are probably. Yeah, they worry that it can cause issues, but in the end, you really have to have, a fair amount of it to get some issues. And it's so uncommon for you to run into it today. So it'd be a problem. Yes, Eleanor.
I forgot if I already said this, but did you know that at the barbershop, basically, they used to cut your wrist?
Mm-hmm.
Because they said you had bad blood. So the thing at barbers, white for bandages, red for blood.
Yeah. Mm-hmm. Yep. Yeah, barbers used to be the surgeons, basically, of their day. If you needed a tooth pulled or something, you went to the barber. And that was part of their job. Because they were skilled with knives and skilled with tools. So barbers used to be the surgeons back in the day. Well, so there was a time that went on actually for centuries where the prevailing medical thought with regard to how the human body functions was this whole thought of humors. And there were 4 humors. There was black bile, yellow bile, blood, and I can't remember the other one, but they would believe that if your humors were out of balance, that was why you were sick. So sometimes they would believe there was something wrong with your blood and they would bleed you. Don't they what? Yeah, leeches too. So back to Leyden jars though. So Leyden jars, so they contain water.
One thing that they used a little bit before that was they would drill a head. So they would drill a hole in the top of your skull, stick a stick in there and stir it.
Oh, that's later. That was later on. That was more like 1930s, 40s, 50s. That was the lobotomy. We'll talk about that in biology next year. Yes.
In the Stone Age,
Yeah, Drew.
if you had a headache in the Stone Age, they would drill a hole in your head. Some people survived. A lot of times they didn't.
Yeah.
They would just drill a hole in their head. I would say the majority of the cure for a headache.
So what you're talking about, Drew, is something that came later, and actually, it's relatively contemporary because there are people. John F. Kennedy, who was president. His sister had a lobotomy. That's how current it was. We're not talking like long ago. So it had to do with psychiatry and it was surgery. Yeah, they believed that. So hang on, they didn't understand neurology all that well yet. They didn't have the imaging that we have available, and they believed that your brain there were connections in your brain, and that was some of that was what was causing mental illness, and that if they broke that connection, it would break that habit, which kind of makes sense if you externally. So yes, they found ways to go in and like sever parts of your brain without opening your head. So yes, sometimes they did through your temple, and sometimes they actually did through your eye. Yeah, terrible. So anyway, and some people like Rosemary Kennedy, she became pretty much non-functioning after that. She just sort of sat there and stared. She was not ever herself again. So anyway, in 1746, the Leyden jar was independently invented by physicist Peter van Musschenbroek. I'm sure I said it wrong. And or his lawyer friend, Andreas Cuneus, in Leyden in the Netherlands. So Leyden jars could be joined together to store electrical charges. So this is like building a battery from small cells, right? That's basically what they were trying to do here. So Senya, I know you came in a little late. We're just going over some history to give perspective. So in 1752, then we had Ben Franklin with his lightning and electricity with his kite experiment, the key. And then this is the guy I have an amazing video about that we'll watch only if we have time.
Luigi.
And yes, his name is Luigi Alonso Galvani. And so in 1780, hang on, he was an Italian physician and physicist. And he discovered that muscle and nerve cells produce electricity. So he had a lab where he kind of dabbled in everything. So he had a team in his lab working on some electrical experiments, and he was dissecting a frog. And his scalpel picked up some static electricity. And when he touched it to the frog's leg, the frog jumped, like its legs moved, because your muscles and your entire body functions on electricity. Your nervous impulses are electrical. The fact that your muscles move is electrical. Everything's electrical. So he was the first person. So basically what he ended up doing was building, Andrew, he built like a biological battery using a frog leg, but he did crazy stuff. Like, no joke, he had a cast iron fence around his house. And during electrical storms, he went out there and he hung frog legs all over the fence. I mean, the guy is like, this is wild. But I've done similar experiments in lab in college, and it is pretty fascinating. You can get muscles to move, heart muscles as well. I've done it with heart muscles and leg muscles, and it's pretty cool. So if we have time, we'll watch a video on Galvani because this is a wackadoodle fun.
We should do devil's toothpaste.
Oh yeah. It's like elephant toothpaste. Yeah. What were you gonna say?
That's actually really dangerous.
We did that sort of at the very beginning.
Elephant toothpaste.
It gets hot.
Devil's, it's not the heat. It literally explodes so fast.
What were you gonna say?
Explodes vials.
Did you have something to say?
Yes. Don't they use on your body if you died? Find out how you died. They use electricity.
Yeah. So you've seen those probably.
Don't they regurgitate?
They say AED on them. Now they have them in hospitals where they're on a cart, but if you're in public places, you may see like a white box with the red letters that say AED, and those are automatic electric defibrillators, because doctors will put them on you and they'll say clear and everybody moves, and they will send an electric charge through your body, which can kind of jumpstart your heart again if it has stopped. But the automatic ones, these ones that you see on walls in places, like we have one in our church, it's right on the wall, it says AED really big. So how those work is you start it and it has a voice that speaks to you, a computerized voice, and it tells you exactly what to do. And you put them on a bare chest of the person, and it will tell you back away, and you back away, and it will do all the work for you. You don't have to push any buttons. So it's kind of idiot proof, which is great. Oh yeah.
Idiot proof.
So this is the guy we get. You ever heard the word volt? I know you've heard it. How many batteries? You have a 9-volt battery, right? This is where it comes from. And he has my favorite name. His Count Alessandro Giuseppe Antonio Anastasio Volta. Great name. So that was from yes. Yeah, we'll just call him Volta, but it's Count Alessandro Giuseppe Antonio Anastasio Volta. So from 1745 to 1824 is when he lived. And he developed the first electric cell, which he called a voltaic pile. And that was in 1800. And you can see a picture of it there. It kind of looks like a bunch of watch batteries stacked on each other. So a voltaic pile consists of alternating layers of 2 dissimilar metals separated by pieces of cardboard soaked in sodium chloride solution or sulfuric acid. So think about that. Sodium chloride solutions, we've got a salt solution, which means we have ions, so we have some free floating electrons. And when you use an acid, you get all those protons donated that are freed up, which means the electrons are also freed up. So these are both good things to use. It makes perfect sense. So this is his voltaic pile here on the right. And this is a voltaic pile at the Smithsonian that they've got as an example of an old school one. It's pretty darn cool, actually. So then we get to 1800s. Now we're getting much more contemporary, right? 200 years ago. So in 1800, and we haven't even had the Civil War yet, right? Chemist, this English guy, William Nicholson, he's got a fairly normal name, 1753 to 1815. And a surgeon named Anthony Carlisle, so that's 1768 to 1840, separated water into hydrogen and oxygen by hydrolysis, which is what we are doing in lab today. And it is super freaking fun, no joke. So then we had, whoop, I clicked it. Then we have Johann Wilhelm Ritter, and he repeated Nicholson's experiment of separating water. And then he discovered the process of electroplating, which you guys read about and did a little research on, right? Or looked around your house. So he also observed the amount of metal deposited and the amount of oxygen produced during electrolytic process depends on the distance between the electrodes. Okay, so these people, a lot of these guys, you probably noticed, most of them are men, most of them look fairly well dressed. So these are dudes that had the time and money to spend all day fussing around and experimenting. So
Living the dream.
they had a life of luxury, and because that, they had the leisure to do these experiments, which is good because without them, we may have been many more years behind. But
if some other people had this same thing, we could have probably advanced further, I would say, just because we're not.
yeah, but it means, you know, they were able to pay other people to do all their menial stuff. They didn't have to worry about being out there, you know, in the field digging up potatoes. Now, we'll get to a guy in biology next year who they sometimes refer to as the father of genetics, and he was actually a monk, and he was a gardening monk. That was like his big thing. So Humphrey Davy is the last guy. I love the name Humphrey. Humphrey Davy from 1778 to 1824 utilized this voltaic pile that our Count Volta made. And in 1807 to isolate elemental potassium by electrolysis, which was soon followed by sodium, barium, calcium, strontium, magnesium. So he figured some stuff out. So then we get to Faraday. Faraday is awesome, by the way. So Faraday's, Faraday cages, yep. So yeah, Faraday from 1791 to 1867. And he began his career as Davy's lab assistant. So he hung out with Humphrey all day. And in 1834, so still pre-Civil War, right? He developed two laws of electrochemistry. So the first one is the amount of substance deposited on an electrode of an electrolytic cell is directly proportional to the amount of electricity passing through the cell. And then the second one was that the quantities of different elements deposited by a given amount of electricity are in ratio of their chemical equivalent weights. So he had some time to do some stuff. Now, if you look up Faraday and you look up videos on Faraday on YouTube, I recommend you do this. You'll see, what?
I just
Yeah.
remember the words chicken coop and, Faraday.
You'll see a Faraday cage, and a Faraday cage is kind of a cool thing. And he is on English money. There he is. He's on a 20-pound note. Ta-da.
How did he just like bribe them? Like, hey, yo, you should put my face.
No, they put, like we do, people we think are important on the money. So he defined a number of terms. He defined anode. You've heard of anode, right? So an anode is the surface at which the electric current, according to the present expression, enters. It's the negative extremity of a decomposing body. So basically, when you're looking at a battery, the anode is the negative part. And then the cathode is the positive part. How do you remember that the cathode is the positive part of the battery? Do you remember? So you remember that the cathode is the positive part of a battery because if you remember that cations and cathode are positive, then you just say it's positively adorable, and you picture a little cat in your head and you think the little cat is positively adorable, and you won't forget that your cathode is where your positive end of your battery is. So on a 9-volt, and this one has some corrosion, which is what I was going to show you, they're labeled plus and negative, but on the 9-volt, it's the little button, not the snappy part, like the inside, not the outside part. And on most like regular DA batteries, it's the button part, not the flat part. So many bodies are decomposed directly by electric current, their elements being set free, and he called that electrolytes. So he's given us a lot of words. So he also said, I propose to distinguish such bodies by calling those anions, which go to the anode of the decomposing body, and those that go to the cathode are cations. So then he said, when I speak of them together, I'm just going to call them ions. So this dude basically spent time in his lab and was like, I'm gonna make up some words because I'm experiencing some stuff and there aren't words. mean, I'm gonna call these anions and cations and anodes and cathodes because I feel like it. Like, it's not like he's basing it on anything. Those are just totally his own words, which is cool. So the chlorine of lead is an electrolyte when electrolyzed, all this stuff. He had lots of fun in his lab, apparently, lots of time. So then we get to Daniel. So
That's the dumbest thing.
John Friedrich Daniel, and he was a professor at King's College London, which is still there and highly respected. So now he lived from 1790 to 1845. So Daniel's research into development of constant current cells took place at the same time in the late 1830s that the commercial telegraph systems began to appear. So we don't even have phones yet. We're getting telegraphs. And this dude is like, I can make a constant current of some kind. So this is pre-Edison, pre-Tesla. This is way back in the day. So Daniel's copper battery in 1836 became the standard for British and American telegraph systems. And then in 1839, he experimented on fusion of metals. With a 70-cell battery, he produced an electric arc so rich in ultraviolet rays that it resulted in an instant artificial sunburn. Awesome fun. And these experiments caused serious injury to Daniel's eyes, as well as the eyes of spectators. Ultimately, he showed that the ion of the metal, rather than the oxide, carries the electric charge. So here are some of his early inventions. And I have a funny little meme. It's just a weird picture of Daniel and Faraday. I'll have to show you. It was just, I saved it because it was goofy when I was looking online. So now we're getting more contemporary. 1864, 1941, we have Nernst, Walter Hermann Nernst. And he did some more electrochemistry experiments that were inspired by Arrhenius, which was way back in the day. So he worked on this whole electrolytic pressure of dissolution theory. But basically, he has an equation named for him, and it's called the Nernst equation, and it relates to the voltage of a cell. And he's contemporary enough that we have a photograph. Okay, so we're getting, which is nuts, because here we are, like, using a computer, projecting it on the TV. And did you see what year he did this in? Look at what year he did this in. 1898. So just over 100 years ago. Not that long ago. This is when, we're not even getting to electricity in your house yet. That's pretty incredible. So terminology, here's our Faraday dude. I freaking love his getup here. First off, the bow tie is spot on. It's huge and it's amazing. Secondly, the vest and the pocket watch chain are really awesome. And thirdly, that coat. And none of it would be amazing without the hair. You have to have the hair. And this guy, man, he had it going on. He is stylish. I like the look here. So we have voltage. Here's some terminology here. So voltage is the potential difference, okay? The potential difference between two half cells, and it's also the energy that drives a reaction. So what kind of battery is this? Do you know what it's called?
I'd say
We actually call this one by its voltage. Like, so we call some A's, D's, triple A's, whatever. This is actually a 9 volt. We call it a 9 volt because it actually has 9 volts. So it's I know, you can't stick them to your tongue. It's gross. No, this one's already been through some stuff. It's all corroded.
It's kind of heat. You stick it to your tongue, it'll tingle.
It will, because it'll pass electrons right through your tongue.
Not too much dangerous.
No, but it's gross. So anyway, the voltage is the potential difference. So remember, differences are subtraction problems, right? Oh, here he comes with the bone again. So if you know how much you can get at one end and you know how much you should get at the other end, then if you subtract one from the other, that's the difference. So the potential difference is voltage. So that's if everything works. So your current is your flow of electrons, and high voltage doesn't necessarily mean high current. You can have low voltage, high current. Current's just that flow. How fast are they flowing? And then you've got primary batteries. So these are non-rechargeable. These are what we call galvanic cells, right? And then we have secondary batteries, and they are rechargeable, like lithium-ion batteries. So your cell phone battery, your laptop battery, these are rechargeable. When your batteries in your walkie-talkie die, they are dead. You ever had a little kid around who has a toy, and the batteries are slowly dying, and like the toy will talk more slowly, or eventually it just dies, and you're like, thank you, Lord, it's dead. It's not going to make any more noise. Yeah, those are for primary batteries. And then you get tertiary batteries, and these are fuel cells, which are entirely different. And sometimes you don't even really consider them batteries. So here is a galvanic cell, and this is what they look like. They have a salt bridge. So in here, all this stuff is going on. And actually, if you take a 9-volt battery apart, it's like a stack of watch batteries. It's kind of weird. Maybe I'll do that while y'all are doing your lab. So galvanic cell induces a spontaneous redox reaction, which is what we did last week. Remember, we did redox in lab, and it creates a flow of electrical charges or electricity. And non-rechargeable batteries are an example of galvanic cells.
Super efficient.
Hmm?
In my opinion, I just like the rechargeable plastic.
The rechargeable ones, yeah, they're pretty cool. So you got electrons that flow from the anode, and they're negative since electrons are built up there, and then the cathode, which is positive. Remember that positive cat is positively adorable. And then your galvanic cell produces an electrical charge from the flow of electrons. So this is how they work. So here's batteries that you've seen before. Those I think are Duracells and Energizers because they're silver and gold at the top. They look familiar to me. So you got many examples of galvanic cells that are power sources that generate electrical energy from chemical energy. So these are all chemical cells, right? So all these non-rechargeables, A's, double A's, D's, C's, these are all galvanic electrochemical cells, right? They all produce electricity from chemistry, which is kind of cool, right? You can just put some chemicals together and poof, you have electricity. And fuel cells differ from batteries in that they're oxidizing and reducing agents or gases. So this is what I was saying before, they need constant reactions. So conventional batteries, which supply energy from chemical reactants stored within them. When these reactants are consumed, the battery's dead, right? An alternative approach would be to feed the reactants into a cell as they are required so as to permit the cell to operate continuously. So that is the fuel cell idea. So a fuel cell doesn't die because you keep feeding it more reactants so that it can continue to make more products. But
don't die because you keep feeding them.
yeah. And the ones like these that you buy at the store, they die, right? Because they only have a limited supply of reactants. And when it's done, it's done. So fuel cells were not employed for practical purposes until space exploration in the 1960s. And it says the principle was first demonstrated in 1839 by Sir William Grove, a Welsh lawyer and amateur chemist. Again, he's got money, so he has time to fuss around with stuff, right? And at the time, it was already known that water could be decomposed into hydrogen and oxygen by electrolysis, which is, again, what we're going to do today. And he tried what he called reverse electrolysis, which is combining hydrogen and oxygen into water, causing a potential difference to be generated between the two electrodes. So we are going to do that today. It is synthesizing water. And we call that condensation when you synthesize water. But we are going to not only split water into hydrogen and oxygen, we're going to split it, we're going to combine it back again and make water, which is very, very cool. So it wasn't until 1959 that the first working hydrogen oxygen fuel cell, and that was by Francis Thomas Bacon in England. A lot of these guys are English. I don't know what's up with the English and batteries and stuff, but it's a grand tradition. So although hydrogen has the largest energy to mass ratio of any fuel, it can't be compressed into a liquid at ordinary temperatures. And if it's stored as a gas, the very high pressure require heavy storage containers, so greatly reducing its effective energy density. So some materials are capable of absorbing large amounts of hydrogen, and they can reduce the required pressure. So other fuels such as alcohols, hydrocarbon liquids, which we're learning soon, coal slurries have been used. And methanol appears to be the most promising. So methanol, if you remember, that's the alcohol you use like in an alcohol burner, which that's what we used when I poured it on the counter and then I lit all those chemicals on fire and they all burned. Yeah, that was methanol.
You can pour alcohol on the counter.
Methanol is a type of alcohol. So then we have galvanic corrosion. That's what this is. So this battery I actually used last night to do the same lab you're going to do today. I just wanted to test it, make sure it worked. And I got a lot of corrosion. And it's kind of blue. If you want to pass it around, you can. Let me show them first. So it's kind of, whoop, that's bad. Kind of blue. Why do you think it's blue? What do you suppose is in it? Just don't touch that part. Pass it around. Don't touch the corrosion part on top, but you can look at it. So usually when you see blue,
I know.
what?
It's not bluish, it's more greenish. It's like copper.
Yeah, it's copper. Very good. That's exactly what it is. It's
The
copper.
Statue of Liberty used to be copper color.
Yep.
It used to be
Yeah, Statue of Liberty is bronze actually, but she looks green to us because she's not clean. She's oxidized.
Why shouldn't you touch the top?
Well, because that's the corrosion, and sometimes there's some acid and stuff that get in there.
Don't they clean her every now and then?
They do. So whether there is, hang on, we're watching time, so hold on. So whether there's electric current or not, electrodes of a cell have different potentials, and the difference between them is the voltage. So let's see. An electrolytic cell is a cell which requires an outside electrical source to initiate the redox reaction. So the process of how electric energy drives non-spontaneous reaction is called electrolysis. Whereas the galvanic cell uses a redox reaction, the electrolytic cell uses electron movement to cause the redox reaction. So electrolytic cells like these are the kind that can be recharged, and they require some outside electrical source, which if you think about, makes perfect sense. You plug it into the wall, you get an outside electrical source, it builds up charge, you're good to go, right? Your phone, your computer. So there are equations that go with it that you guys don't really need to worry about too much. And they remove electrons from the anode, and that's how they drive this whole oxidation process. And they turn electrical energy into chemical energy and then back into electrical energy again. Whereas these kind of batteries, galvanic batteries, just turn chemical energy into electrical energy. Electrolytic cells go electric to chemical to electric. Busy, aren't they? So here's an example, your little lightning cable, right? So here's your common ones: phones, MP3 players, computers, anything rechargeable. My husband's drone, all that business, right? And in electrolysis, a compound is decomposed, and it's usually into hydrogen, oxygen, aluminum, sodium, chlorine. These are the kind of things you see. So we're going to be decomposing water in electrolysis today. And it's a process when electrons are forced through a chemical cell, thus causing a chemical reaction, right? And the positive charge usually attracts electrons. So today, when we put this in water, which is what we're going to do, and we're going to put some ions in there by using some salt. When we put it in the water, it's going to start conducting between the two, and the electrons are going to start flowing out, right? But we are going to put test tubes on top, and one of them will have hydrogen coming out, and the other one will have oxygen. We're going to make gas. We're going to make hydrogen and oxygen. We're going to create it from a battery and water.
So are we gonna make water?
Then we are going to make water. We're going to go back again. Yep. So then we talked about electroplating. So you guys read about electroplating.
Inefficient way to just make water.
And let's see. Do I have time to? Okay, let me show you this one. I don't think we have time to watch the whole thing, but I want to show you this before you guys tell me about the electroplating you found at your house, because this is a cool how it's made, which I could watch all day. But this is how it's made on electroplating.
Plating is a layer of metal coating an object of a different type of metal. The purpose can be decorative, as in silver plating.
Yeah. Show me how it's done.
That was a penny.
Do it for me.
I wrote down a penny.
A penny. Okay, yeah. So here are some things that they electroplated, but you need to watch them actually do it.
Yeah, they did.
So here they go.
Vat of boiling chemical solvents. As the hot vapor comes into contact with the colder metal, it condenses, dripping down into the vat and taking any contaminants along with it. The remaining solvent residues evaporate, leaving the parts squeaky clean and dry.
It's another clean.
Next, a worker wearing protective clothing sandblasts the parts with aluminum oxide powder, a strong abrasive. This roughens up the surface so that the plating metal will adhere better.
Yeah.
The most common
Plate
plating
it.
metals.
So here they go.
The plating process is called electroplating because the key to it all is electricity. They start by tying strands of copper wire to a copper support frame, copper being the best metal for conducting electricity.
So they hang these pieces on this frame,
Steel parts they'll be
and then they end up dipping this frame into this bath with the ions.
They do the electroplating in a tank. After filling it with water, they add a handful of chemicals to help conduct electricity.
Lots of salt, probably some
because
acid.
water alone won't conduct it sufficiently. Along the side of the tank in bags
Mm-hmm.
are metal baskets. They contain bars or balls of the plating metal. In this
You
case,
also get hit
cadmium.
these amounts of the dangerous stuff.
Workers connect the support frame of the steel parts to the negative terminal of an electric source.
So they're running electricity through that bath now,
The positive terminal.
and the metal is in those bags.
On a steady DC current, no stronger than 6 volts. The electricity dissolves the cadmium, lacing the particles with a positive charge. They travel through the water and attach themselves to
Pretty
the
cool.
negative charged steel parts, creating a smooth and even layer of cadmium.
So now they got cadmium on there and they'll rinse it off. But that's pretty awesome. So I would love to know if y'all can share with me. I think the galvanic and electrolytic cell were probably pretty easy for you guys to find, right?
Battery and
Yeah, battery in a phone, something like that. I would love to know what your metal plated objects were. You said a penny.
Yeah, that's what I
Yeah, pennies only have copper on the outside. They're nickel on the inside, yeah?
I didn't really have. I didn't have internet access, so when I did,
Oh, okay.
I wasn't, doing chemistry really, so I just did not watch the video. Sorry.
That's okay. So, for this, did you get this done? Did you get the homework part done? You're good. As long as you get this done, and you can always send it to me later if you need to go home and look. So, who found something?
I put down a penny, like a coin, and I put, what was it?
What was the other thing? Who found what? What'd you find, Jules? Did you find anything electroplated at your house? What'd you find?
Silverware. That was the other thing.
Okay.
So yeah, a picnic table, and I chose the legs of the picnic table because
Oh. Okay, metal plated legs. Cool. What else?
I didn't watch the video, so this is kind of guessing. What like a doorknob be?
Sometimes doorknobs. Yep. Sometimes.
What about a car? Like, would they just?
Sometimes the chrome is
Mostly
plated.
alloy or
What else did we find? Anything else?
Jerry.
Earrings are sometimes, yep. And sometimes you get silver.
What about just appliances?
that thing right there.
What now?
Those candles.
Oh, those?
No, below them.
Oh, these?
Yeah.
I think that's actually solid.
What about like just around the house things like I don't know the oven?
Mm-hmm.
I think I have
The oven's
bracelet made out of metal.
Well, very often things are silver plated or nickel plated or brass plated or whatever. So yeah, very cool. All right, so I'm gonna let you two go now. You guys have this lab for you to do, and you should be able to do the whole thing. You're gonna need some distilled water, and you're gonna need a measuring cup. But it says that on your paperwork. So you ladies go ahead and do that. It will be fun. I promise. It'll be cool, and it'll start really fast. Like you'll be surprised at how quickly your reaction happens. It's really, really neat. So you guys work on that, and I'm gonna get them started on lab. We'll see you in 2 weeks because we have spring break, right? Oh, and one more thing. I have an assignment in Teacher Ease where you sign up for your element. And it should be available to you today, I believe. So you'll see it show up as a new assignment, and everybody should go in and pick their element. Okay.
How do you know which one's your element?
Right?
You
You
get to choose
pick it?
whichever element you want to use for your final project. It's up to you. Just as long as you pick one that somebody else hasn't already picked.
What's it called?
Okay.
Cool. All right, you guys. We'll see you later.
Bye.
Bye.
Water.